Optimizer Fundamentals. After completing this lesson, you should be able to describe each phase of the SQL statement processing, discuss the needs for an optimizer, explain the various phases of optimization, and control the behavior of the optimizer. So we want to give you an overview of the optimizer to enhance your knowledge about the basic techniques we talked about. And then we'll later on get into more details once we've had a look at different ways of capturing execution plans and interpreting the execution. Then we'll delve into more deeper understanding of the different operations the optimizer does later on. But first we need to get through the basics. So in this lesson we have a group of topics we want to have a look at. So we're going to start with SQL statement representation. Okay, so we're running the SQL statements on an Oracle database. Okay, in reality, how well the Oracle database is tuned impacts how well your SQL statements as a developer that you wrote for the application run, and then vice versa is also true. How well you write your SQL impacts the performance of the data. We tried to process the SQL as efficiently as possible, and most of our tuning goals in this course, except where we note otherwise, are around an OLTP application, online transaction processing, that generally has an index for everything, and we expect to do very short SQL, return one customer order if it's an order entry application, insert one order, update one order, insert one new customer record, instead of doing a lot of batch processing. Sometimes in the background it does batch processing to do a group of these, but for the fundamental operation, we expect to have an index for everything, and everything should probably take less than a second generally to execute. Okay. Some of the statements we have seen up to now in the basic section, we're leaning towards the end to more data warehousing type queries, which took a little longer than the second we expect. And in a pure OLTP, we're going to have a finite number of transactions, and each transaction has a finite number of SQL statements. And what we want to do is share those SQL statements as much as possible. Particularly if we can use bind variables, we can share them. So we can have multiple user sessions or processes executing the same SQL because they're executing the same transaction, or sometimes one SQL statement is used in multiple transactions. Okay. And we want to optimize the storage, so we'd like to share the execution plan once in the shared SQL area, which is actually in the SGA of the database. But as each of these processes are executing the same statement, they need their own private area to manage that execution, to know where they are. One user may be checking if the statement is in the shared memory, doing a parse to find that. Another statement may be in the middle of executing it. Another user may be fetching the data from the database. So they're all in different phases of their particular execution. So the execution needs to be tracked individually, and we put that in a private area, which is actually part of the program global area for the process. And it's really its own private work area to track the details. We have a second statement B. It has a representation in shared memory. A group of users can share that representation. Our goal is to parse it once and use it many times if we can for a pure OLTP application. This is just drilling down and showing you a little more details of the database. The more you understand the database, the more informed decisions you can make about how your SQL is running and how we might improve it. So more knowledge is always better, in my opinion. So there is an appendix to this course that has a more detailed overview of the architecture of the database. I really highly recommend that you review that as part of this course. Okay, that's a very good suggestion. But this is a quick overview. The shared area of the SQL statements exists within the system global area. And the system global area in reality is nothing more than a large cache. And we break the large cache into a number of subcaches. And of course, the reason why we use caches, generally in computer technology, is we're looking for an improvement in performance overall. By caching things and sharing them, then we can reduce the cost of running the database. So we have different caches. One of them is the database buffer cache. We cache blocks that we're working with, particularly if we're changing the blocks in the database buffer cache. We have a redo log buffer as another cache. It's really a change record of changes made to an Oracle database. And we have some other specialized caches. If you have the Java option configured against the database, we have Java Pool, and we have the Oracle Streams. What we're interested in is the things that influence these. These actually influence your database, but not quite as directly as the shared pool. Because the shared pool is a large cache that has a whole group of subpools in it, which acts as subcaches. So we have major caches, and the shared pool is one of the major caches. And a lot of these are very specialized. The database buffer cache is just specialized for handling blocks. The Java pool is specialized in handling the classes that Java needs to use. Interesting enough, Java uses a fair bit of shared pool also when it runs. But in the shared pool, we have a group of subcaches, and there are a large number. We never discuss all of them on any of the classes that I'm aware of. And these are important. The ones we show here are important for your SQL processing. One of them is the data dictionary cache. When we need to go and parse a select statement, we need to know the definition of the table or tables. So it's a select from employees. We need to know that there is an employee table. Okay. If we say star, we need to look up what the star represents. If you list a group of columns that applications should really do, applications don't need all the columns at the same time generally. They should list just the columns they need at a particular point. Then we need to confirm that those columns exist and what data types are they and what are the rules around using them. And we get that from the data dictionary. It lives in the system table space, but we read it into its own cache called the data dictionary cache, and it's actually rows out of it, and it's actually called $row cache. They load rows out of the row cache. We could have put the blocks for the data dictionary cache and the database buffer cache to share them, but we actually tend to get more shareability of the data dictionary than we do of the blocks. So we gave them their own cache basically. The second one that we're going to talk about in a fair bit of detail later on, okay, is the results cache. That was a new feature we added fairly recently to the database, okay, back in 11G, that allows us, if we have a query that we execute repeatedly because we got to check to make sure something hasn't changed, but it really doesn't change very often. Every time we execute it, we have to execute it out of the shared pool. It takes CPU cycles to execute it. If for long periods of time it returns the same information, why don't we just execute it once and store the results somewhere, and we have the result cache for that purpose. And then we'll keep serving it out of the result cache unless somebody does DML to the table or set of tables that the results are based on, and then we'll flush the cache and the next person will really have to execute again. Because once somebody does DML, we expect the results can change. So flush it, have somebody re-execute the SQL to repop it. And that can reduce, another way of reducing the CPU cycles to support sophisticated applications. There's lots of areas where you have to look up reference data that may not change for large periods of time. The other area that we're really interested in the library cache, that's the area where the shared SQL statement goes, okay, when we go in and actually process it in there. So we're intimately concerned, and one of the things we need to make sure that for our database, this is sized reasonably for the number of SQL statements. If it's undersized by making the shared pool too small or making the SGA too small overall, then we may do extra parsing. We use an LRU list in a lot of these areas to manage them. If we run short of memory, we've got it filled up with statements we're processing. Our theory is take the one you haven't touched the longest period of time and remove it to replace it. If you haven't touched it for a long period of time, you might not touch it again. If you just worked with it, there's a better chance you're going to reuse it in the near future. Is it a perfect algorithm? Nope. But it's the best one they could come up with up to date. Okay, so we could age it out and then a little while later need to execute it. It would cost us a hard parse to bring it back into the library cache overall. Now, while we're sharing these, we said we could have multiple processes executing the same statement. They can share the execution plan to execute the statement, but they need to control where they are in their processing, what results they returned, etc. So they use private SQL areas. They can be managed individually with old parameters, but starting in 9.2 of the database, we introduced a new way. What we need to do is specify an aggregate target for the sum of the PGA, and it's really the sum of the tunable portion of the PGA that we want to use in the database. Of course, the target is a target if we express it as a target, okay? And then it can actually go over a bit. And on an OLTP, it goes over a bit. We've experienced on data warehousing, it can go over substantially. And then it will eventually come back down, depending on what SQL are being processed and which resources they actually need. The one advantage of using the SGA aggregate is that if the operating system supports it, we can move memory between processes. We can take memory from a process that's only doing simple things, doesn't need much work areas to process the SQL, and give it to a process that needs more. So it gives us some more flexibility around tuning the PGAs dynamically, okay, in the environment. So the next thing we want to look at is the SQL statement processing. How does it take an SQL statement and get to the point where it can actually execute it? So it needs to process it, and this is the overview. User submits the request. He usually does it from a client tool. It gets sent to his dedicated server, and we call it a dedicated server because there's one dedicated for each client. If I have 50 users using dedicated servers, there's going to be 50 dedicated servers. Okay, the user application submits the SQL statement to the dedicated server. The dedicated server needs to process it. The first thing we need to do is to do a syntax check as part of an overall parsing process. We got to make sure that Trevor can type select star correctly, get the syntax right. That's always a good thing. Okay, if not, we'll just get a syntax error from SQL. And those errors we can catch up front. It also does a semantics check. Is there really a table T1? And what does the star mean? And we also do a check to see if Trevor has privileges to access T1. If it belongs to the schema, the account that Trevor logged into, then Trevor has full privilege. If it belongs to somebody else, somebody has to grant me privileges to access it, because by default, another account doesn't have any access to it. And then once we check that it looks semantically, and Trevor has the privilege to execute on the T1 or whatever the table is, if he doesn't have privileges, we stop there and tell him he's got a privilege problem and don't have to do anything further. But if everything up to here checks out, okay, it does a soft parse. And what it's really doing is checking to see if in the shared pool the SQL statement exists. It does that by taking the full SQL text and applying a very simple hash algorithm, just taking the text in the base character set of the database and hashing it to a memory location. Now, because we only have a finite amount of shared pool, and we could have lots of statements, theoretically we could run, more than one statement can actually hash to a particular memory location. So what it actually hashes to is a hash header. And off of that, we store 0 or n SQL statements that actually hash. There could be none out there at this particular time. Might be very common if we first started up the database and we're just starting to run the application to get the shared pool loaded. It could be 1, could be 20 statements hashed to the same location. And then once we find the list of statements, we take each statement in the hash list that hashes off the header, and we do a text comparison character by character to see if they're the same. If we find the statement in where we expect to find it, we consider it a soft parse. We had to go look for it, but we consider it was successful. We avoided the hard parse, which is the process of building the execution plan. Okay? And one of the side benefits of doing the initial stage is that we parse the statement into one or more SQL blocks. An SQL block is a statement that can be run standalone. A statement that can be run standalone from the main query is a non-correlated subquery. It's a inner query we execute once and then feed the outer query. So the inner query can be treated as one execution block, and the outer query can be treated as another, and they can be optimized independent of each other. If it's a correlated subquery, that's no longer true. They have to be optimized together, because for every row in the outer, we have to execute the inner query. Now we execute the inner query multiple times, so we treat them as a single object in that case. So it builds a representation as query blocks, and then we pass those representations. For my simple statements that I demo a lot, they're a single query block in most cases, except for some of the correlated subqueries. Okay? The optimizer will take that input as valid statements that need to be optimized if we couldn't find it in memory. What it's going to have to do is discover it wasn't in shared pool. Then it's going to have to allocate a new chunk of memory of shared pool to it. There is a latch, a high-speed lock on the LRU list for the shared pool so that it can acquire some memory, takes the latch, gets memory. It may have to age out some statements to free up memory. If there's available memory, it's a little faster for it. And it will allocate a new area to store an SQL statement within the shared pool. And then it will go through the optimization phase. Okay? It will take a look at the SQL statement within about a second. We artificially limit it to about a second to process the statement, and it will come up with one or more execution plans. For complex statements, it can come up with many execution plans. For a simple select star from T1, it's going to come up with one. No where clause mean no predicates, mean we can't apply any filters. It means it has to go in and do a full table scan. So really simple to make that decision. So a second is more than enough time, but for more complex statements, we can come up with a number. The optimizer job is, after generating a group of possible execution plans, its job is to come up with what it perceives the best. The optimizer is nothing more than a program. It needs some input. If we give it good input, it will give it good output, like with any program, assuming it's a well-written program. But if you write a good program, you give it good input, you get good output. If you give it bad input, incorrect information, the results aren't going to make any sense. It's going to give you bad output. And the optimizer needs a number of pieces of input. One of them is a query block to optimize. The second thing is statistics on the objects that we're accessing. Whether it be the tables or the indexes, we need to know information about them. Okay, and the optimizer uses that to make a decision. It needs up-to-date statistics collected on the objects to make good decisions. So we'll have a look at that a little later on. We have a little lesson introducing the optimizer statistics. And it will pick what it perceives as the best one, and it will pass it to the row source generator. Okay, row sources are just individual sets of rows that are fed to another step in the execution plan. There's a group of steps. At some point, the data needs to come from the tables on disk. Get into the database buffer cache or into memory somehow, and then we need to process them. We call getting them from disk into memory a physical read. Okay, when they're in memory, we need to process them. So if we read it off of a table, we get, especially if we're joining, we have two row sources. We know how to join two tables. The two row sources could be two tables, the employees and the department table that we want to join together. We access both of them. And then the join creates another row source that can be fed to a later step in the execution plan. And once we pick the best plan, the row source generator is responsible for generating the steps that we either call the execution plan or the row sources that are executed in a certain order to execute the plan. And then finally, we did all this work because we wanted to execute it, so we execute the statement. So going straight down is what we do if we discover it's not in shared pool. Then we have to do the hard parse, which is the optimization, the row source generation, and then finally execute. If the soft parse finds it in memory and it's still a valid execution plan, then we can go and execute it. Okay, and then we can get the results of the query. So what we're hoping is we put it in memory once for repeatable statements and that will cause us to get it into memory the first time, a hard parse. After that, we can look it up using a soft parse. Okay, a little more details around parsing it. So we have to, when we first look at the statement and go to check if it's in memory, check if it's syntactically correct. Is it semantically? We have the tables and objects we're talking about. Check that Trevor can access it, the privileged. We got the privileges to access the objects. And then it anticipates processing a statement. We need to allocate a private SQL area within my process, dedicated server that's processing this. And you have to watch, we use the phrase parse in a couple of contexts, so it makes it a little confusing. We have the parse call that creates a private area. Another way of calling it is a cursor. It creates a cursor to work with it, a work area within my private area to work with the SQL. And it's a generic structure to process any SQL. And that's the parse call allocates the private area and sets up that area. Okay. Then we do a search in shared pool to see if the SQL statement is already in shared pool. If it is, we had to hash it, find the hash header and do a comparison. We found it, yay. Somebody else did the optimization. We call it a soft parse. We can go immediately to the execution. If we don't find it, then we need to allocate a shared pool SQL area for it, a place to put it in the shared pool. And then we need to do the optimization. This is called a parse operation. So notice the difference. The parse call sets up the private area within my dedicated server. The parse operation sets up and allocates, if we have to do a hard parse, allocates the shared SQL area within the library cache within the SGA. The library cache is within the shared pool, and the shared pool is within the SGA of the server. Okay. And then we do the optimization to build pick the best execution plan we could find in a second. That's all really the optimizer can say. With the second you gave me during normal optimization, I found the best plan I could. Quite often, that's more than enough. Sometimes there's a better plan that didn't get a chance to look at. And we can give it more time by doing the SQL tuning advisor will actually allow us to give it more time. Then we could give it minutes and it may be able to find. But during the 1 second, it picks the best one it could find. A lot of cases, it could be the absolutely best, sometimes not, and builds the row source and to actually execute it. And then we're at the execution point. Either way, we get to the execution. Doing the soft parse just shortens it. But the soft parse is used to find it. As part of the private area PGA for my server, we have a couple of arrays in it that we use to keep track of SQL statements. One is the open cursors. By default, it defaults to 50, okay? And it allows us to have the addresses of 50 statements that we have private areas in that points to exactly where they live in the library cache and the shared pool in the SGA. So while we're executing it, we always know where it is. So we don't need to go look it up again. As long as we never close our private area to that, we hold the address to it, we're good to go. Okay, in the past, we had a second parameter called session shared cursors, which we could put anything that was on the open cursor. If we go to execute the first one, there's nothing on the open cursor when my dedicated server first starts. Puts it on the open cursor. It can put 50 more in the open cursor and there's room. And when we go to put the 51st one in, one of the old ones has to be age out. And we used to, in the past, the session shared cursors was set to 0 by default. And it would just forget about the address. And we'd have to do, if we ever needed to re-execute it in the future, it would have to do a soft parse to find it in the shared pool again, which will do the hashing and do the comparison. In current versions of the database, 12c particularly, the session shared cursors is set to 50. So it gives us 50 more slots, and what it will put in is the address, but the address is current if it never ages out. The SQL statement never ages out of the shared pool. If it ages out and gets reparsed, it may get put back in a different memory location. So it has to do a quick check to see if it's out there, and if it does a quick check and it's out there, then we don't need to do the soft parse. So the session open cursors makes the soft parse softer in reality by using arrays to remember where the addresses are. But if it turns out on the session cache cursors, I closed it and everybody else who used it closed it and the server decided to age it out, then the address may be invalid. It tries the address in the open cursors, session cache cursors. Can't find it, then it does the full hard parse to find the new location of it. So it's kind of interesting processing. So SQL optimization. The purpose of the optimization is to optimize the performance of the SQL, find the lowest cost execution plan that the optimizer perceives as the lowest cost. The optimizer attempts to pick the fastest execution plan, or what it perceives as the lowest cost. During the optimization stage, the Oracle database must perform a hard parse at least once for every unique DML statement, either insert, update, delete, or a select statement. And it does the optimization on both types, DMLs and select statements. Just to let you know, DDL statements, data definition languages, are processed differently. It actually doesn't do the optimization steps on this. And this is having a look at the details of the SQL statement processing. So we'll have a quick look at this. Okay, coming up, we give it a statement. So this is a bit of a review on what we've already looked at. And the reason why it's a review, because I went back and forgot. So we'll just skip forward a little bit. So we had a look at this. Somehow we went back.